Test, 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 test. Okay. All right. Welcome back from the long weekend. Today we're going to be looking at a long paper slash blog post by Jürgen Schmidhuber. This guy is one of the original neural network, I would say, professors, but he's also very controversial because he's kind of a stickler about credit assignment and references. And he is known for his constant rebuttals and kind of snarky comments where he always says that some particular idea which is being used in some paper is actually from an original older paper that no one really remembers anymore. So this guy is, I would almost say, the historian for neural networks and deep learning in general. So when he released this kind of long paper here about the history of neural networks, I was like, this is maybe the one paper from this guy that makes sense to read. So let's go ahead and get started. ML is the science of credit assignment, finding patterns and observations that predict the consequences of actions and help to improve future performance. Credit assignment is also required for human understanding of how the world works, not only for individuals navigating daily life, but also for academic professionals who interpret the present in the light of past events. All right, so you can already tell kind of what I was talking about. This guy's very snarky, very sour. He really cares about having the first person who wrote down an idea in an academic journal be the one that gets credited for perpetuity. That's what he's all about. Okay. Modern history will emphasize breakthroughs, in particular mathematical foundations of today's neural networks, such as the chain rule, which apparently is 1676. That's quite old. 1800s was the first neural networks, and then 1965 is kind of maybe the deep learning. Provides a timeline into all of these fields. I'll put things in a broader historical context spanning the time since the Big Bang, when the universe will be many times older than it is now. Is also the draft of a chapter in my upcoming AI book. Okay, so that could be interesting. I don't know if I could read an entire book by Schmidhuber, but I think I'll definitely read this paper. I consider it my duty to promote this document and its knowledge. It means prominently mentioning my team's work. Yeah, I think this guy was kind of broken mentally because there was a famous award and it was given to Jan LeCun, Joshua Bengio, and the third guy, I forget his name right now, but Schmidhuber was really sad about that, I guess, because he wasn't part of that, even though he feels like he made enough contributions to be part of that. So I think ever since that moment, he's kind of become a little darker and more evil, more pessimistic. But I'll stop kind of being a psychologist here and just focus on the actual content. Certain historical events have become more important. Big Bang 13 billion years ago. Completely unknown to Earthlings. Okay. A history of AI written in the 1980s would have emphasized topics such as theorem proving, logic programming, expert systems, and heuristic search. Expert systems being kind of the old version of AI that people had, which was all a bunch of hard-coded if-else statements, basically. Practical AI dates back to 1914 when you had Leonardo Torres y Quevedo build a chess engine. And then AI theory dates back to Gödel from 3134. History of AI written in the early 2000s would have put more emphasis on topics such as support vector machines and kernel methods. Bayesian reasoning, probability theory and statistics, decision trees, ensemble methods, swarm intelligence, and evolutionary computation. The history of AI written in the 2020s would emphasize concepts such as chain rule, deep nonlinear artificial neural networks, feedback-based recurrent networks, before 1956, much of what was called AI was still called cybernetics, with a focus very much in line with modern AI based on deep learning with neural networks. So the human brain has on the order of 100 billion neurons, where each neuron is connected to around 10,000 other neurons. So that kind of, I love reading that fact because it kind of makes you realize that even the largest networks that we have now are just touching that level of scale, right? And even the big networks that we have now, the biggest ones, that have billions of parameters, they certainly don't have 10,000 connections on average per parameter or neuron. And that's another thing too. There's a lot of parameters that don't, right? For example, you have a weight and a bias, but in the brain, when they say 100 billion neurons, each of those neurons would probably take 10 different parameters to like fully describe mathematically. So really, there's another 10x on top of this when you think about how many individual parameters the human brain neural network would have. Your brain apparently learns by changing the strengths of the weights of the connections, which determines how strongly the neurons influence each other and seems to encode all your lifelong experience. Yeah, this is, I'm sure he'll talk about it, but we still, the way we train artificial neural networks is with backpropagation, right, which is basically gradient descent. But that's not really, our brain doesn't do that. Our brain doesn't have a gradient descent algorithm running. It doesn't run backprop when you're sleeping or something like that. It's doing something a little bit more complicated that we don't really fully understand yet. Highlight essential historic contributions. This is a good analogy. Many of the sections mention the later impact of this work in the new millennium, which brought numerous improvements in hardware and software, a bit like the 20th century brought numerous improvements of the cars invented in the 19th. So cars obviously were invented a long time ago, right? But the modern car is significantly better than kind of the 19th century car because of a lot of different things that were invented, right? Like electronics and probably some kind of injection molding techniques and stuff like that. And Schmidhuber kind of makes a parallel here that a lot of this neural network stuff, deep learning, is actually quite old, and like much of the modern success of it is actually due to the kind of improvements in hardware and software that we've gotten over the past like 30-40 years from Moore's law and just general software. Ensuring proper credit assignment in all of science is of great importance to me, just as it should be to all scientists, and I encourage an interested reader to also take a look at some of my letters on the history of aviation, the telephone, the computer, resilient robots, and scientists. Yeah, so this guy is basically a historian. I didn't know he had these kind of things in there. All right, so he starts off with Leibniz. I don't know, I wonder how you would pronounce that in German. Leibniz. So apparently he's the first one to publish the chain rule of differential calculus in 1676. And then you have this other guy here, Guillaume de l'Hôpital, described in his 1696, so 20 years later. This rule is central for credit assignments in neural networks. Why? The most popular neural networks have nodes or neurons that compute differentiable functions of inputs from other neurons, which in turn compute differentiable functions of inputs from other neurons, and so on. So the question is, how will the output of a final function change if we modify the parameters or weights of an earlier function a bit? The chain rule is the basic rule for computing the answer. The technique of gradient descent, which was actually proposed in Augustin Louis Cauchy in 1847. So we're talking 200 years after the chain rule. The stochastic version called stochastic gradient descent, which is usually the one that you SGD that you see. Variants are based on that. Most optimizer variants that you see in modern deep learning packages are based on stochastic gradient descent, not just the original gradient descent. And so the stochastic version was made by Herbert and Sutton Monroe. I think this is I think Rich Sutton is the Sutton that we're most familiar with. So this is a different dude, Sutton Monroe in 1951. Leibniz was the first to publish modern calculus, 1684. Although later Isaac Newton, who I think most people would say Isaac Newton is the father of calculus, because he had unpublished work, so he came up with it too. Their priority dispute did not encompass the chain rule, since they were both building on the 2nd century BC work of Archimedes, who paved the way for infinitesimals and published special cases of calculus for sphere and parabola segments. Fundamental work on calculus was also conducted in the 14th century by Madhava of Sangamagrama, and the colleagues at the Indian Kerala School. Yeah, so it's kind of cool to see that basically neural networks are so dependent on kind of just the basic principles of calculus that if you really want to start doing credit assignment for who deserves credit for neural networks and deep learning, you have to go all the way back to basically Archimedes, because he kind of creates this idea of infinitesimals, and then people start building on the idea of calculus, right? The derivatives and integrals, I think, is kind of the key concepts there. And then eventually you go through Leibniz, you go through Isaac Newton, and you finally get to the stochastic gradient descent, which is kind of a extrapolation of gradient descent, which is an extrapolation of the chain rule. So that's kind of cool. Apparently Leibniz is called the world's first computer scientist. Okay. He designed the first machine that could perform all 4 arithmetic operations in 1673. And the first with an internal memory. I wonder what that even means. He probably he probably just wrote that down. That was just like formulas. There's no way he like built that out of like. I know you can make computers out of just like wooden blocks. Like I've seen that before. Like you can do like addition and subtraction with these like little wooden block computers. You can also make them out of water. But I assume Leibniz was just theorizing on this. His formal algebra of thought in 1686 was deductively equivalent to the much later Boolean algebra of 1847. It is quite remarkable that he is also responsible for the chain rule, the foundation of modern deep learning, a key subfield in modern computer science. Some claim that the backpropagation algorithm, now widely used to train deep neural networks, is just the chain rule of Leibniz and L'Hopital in 1696. And no, it is just the efficient way of applying the chain rule to big networks with differentiable nodes. There are also many inefficient ways of doing this. It was not published until 1970. Okay. So Schmidhuber does mention here that these early versions of the chain rule and gradient descent, they're not equivalent to backpropagation. Going to backpropagation requires kind of an extra step, and that step was not until 1970, which is kind of significantly later. Okay. Now we have the 1800s, the first neural network, linear regression, and shallow learning. So in 1805, you have Legendre published what is now called a linear neural network. So maybe that's the first. I wonder if we use neural network. So neural network from over 2 centuries ago has 2 layers, an input layer with several input units and an output layer. Let's assume the latter consists of a single output unit. Each input unit can hold a real valued number that is connected to the output by a connection with a real valued weight. The neural network's output is the sum of the products of the inputs and their weight. Yeah, so I mean that's basically what we have now. Right, that you have the weights and the biases, you multiply all the weights by the input of that neuron, you add the biases, and then that's what goes out of the neuron. Given a training set of input vectors and desired target values, the neural network weights are adjusted such that the sum of the squared errors between the neural network outputs and the corresponding targets is minimized. I mean, that's pretty much it. You know, you even have the squared error, right? So mean squared error is a very common loss metric nowadays, and the idea of, hey, rather than minimizing just the difference between the output and the target, minimize the squared difference between the output and the target, so that the further they are apart, the more that kind of loss term or the loss is. So I mean, he had all of it here. He had the weights, he had the biases, he had the training data set and testing data set. So there's a lot of concepts here that were that came from Legendre in 1805. I did not know that. Of course, back then this was not called a neural network, it was called the method of least squares, also widely known as linear regression. but it is mathematically identical to today's linear neural networks. The same basic algorithm, the same error function, the same adaptive parameters and weights. So that's kind of interesting there. First famous example of pattern recognition through shallow learning dates back over 200 years. The rediscovery of the dwarf planet Ceres in 1801 through Gauss. So he had a data set of previous astronomical observations, and then trained a little tiny neural network. Literally, at this point, you don't even have computers, so he's doing every single training step by hand, calculating it on paper, maybe with an abacus or something like that, but all by hand. And this little neural network learned to generalize from the training data and predict the new location of Ceres. So that's quite cool. All technical disciplines are required to take math classes, in particular linear algebra, statistics. The so-called greatest mathematician since antiquity, that's what he's calling Gaussian, or Gauss. He also pioneered differential geometry, number theory, and non-Euclidean geometry. Furthermore, he made major contributions to astronomy and physics. So, yeah, I mean, this guy was badass Gauss. Look at him here wearing his little hat and his little frill. So not only is he the guy who made the Gaussian distribution, but he also made the first neural network. He also was kind of an astronomy person, physics person, so this was a real Renaissance man. Johann Karl Friedrich Gauss. Let's look up this dude. He's born in Brunswick in Germany, but at that time it was the Holy Roman Empire. And then he died in actually Germany, so by the time he died it was Germany. 1777 to 1855, so right around the time of kind of the American Constitution, or the American Revolution. Cool. All right, so that's kind of more ancient history. Now we're moving into kind of the more modern age here, 1920s, 1925, the first recurrent network architecture. So like the human brain, but unlike the more limited feed-forward neural networks, recurrent neural networks have a feedback connection such that one can follow directed connections from certain internal nodes to others and eventually end up where one started. This is essential for implementing a memory of past events during sequence processing. First non-learning RNN architecture, the Ising model, or Lenz Ising model. I'm assuming this is a person's name. Yeah, Ising, this guy here, was introduced by Ernst Ising and Wilhelm Lenz in the 1920s. It settles into an equilibrium state in response to input conditions and is the foundation of the first learning RNNs. So RNNs, I don't know if this was a great explanation, but basically it's like when you, a neural network performs inference runs, right? You give it an input, you feed it through all the neurons, and it'll give you the output. In a recurrent neural network, what you're doing is that not only are you giving it the input, but you're also giving it the output of the previous step. So basically, you're performing a bunch of inferences in kind of succession, and you're feeding the output of previous inferences into the current inference. So it's basically taking the basic idea of a neural network and then adding this time dimension and then allowing basically information to flow from earlier points in time to the current points in time. And that's what recurrent, that word recurrence means in that context. They're actually not super popular anymore. There was a period where they were quite popular, and there's a bunch of different variants of these types of things, like LSTMs, which I'm sure he'll talk about later. But nowadays, you just use attention mechanisms with transformers where you just feed the whole thing. You feed the whole sequence, and then you basically do this attention matrix where every element of the sequence is multiplied against every other element of the sequence. So now I would say the kind of transformer architecture has kind of retired the recurrent neural network, although there's still plenty of real world production use cases where you have the kind of idea of recurrent neural networks where you have this kind of like output gets fed back into the input. So they're not dead, but they're not as popular as they were, or as people thought that they were going to be. Okay, 1972, we just skipped over the whole atomic age here. Now we're going straight to the kind of early computation age. You have this guy, Shunichi, made the recurrent architecture adaptive such that it could learn to associate input patterns with output patterns by changing its connection weights. This was the first published learning artificial RNN. 10 years later, the Amari network was republished. So it's this guy here. Some called it the Hopfield network or Amari Hopfield network. It does not process sequences but settles into an equilibrium in response to static input patterns. Remarkably, already in 1948, Alan Turing wrote up ideas related to artificial evolution and learning recurrent neural networks. So you have the OG Alan Turing. This was published many decades later, which explains the obscurity of his thoughts here. The famous Turing test would actually be called the Descartes test. Yeah, so, I mean, this to me is part of the problem of what Schmidhuber's trying to kind of do here with his credit assignment and his like focus on assigning ceremonial importance to the first person to kind of formally come up with an idea. And because the reality is that humans don't do that. Humans, like, we basically consume information and then we just like shuffle it around in our brain and then we just put it back out. So none of these guys, Turing, Amari, like these guys are not necessarily coming up with original ideas, right? So like if Turing writes a bunch of ideas in his dictionary or in his little journals and then they never get published, and this guy Amari like comes up with it in between, then like I don't know why worry about credit assignment here, right? It's like Turing and Amari were probably both reading the same types of texts and then they both came up with the same idea, right? It's like this in nature. You'll see this. You'll see how the crab form was actually evolved 6 different times in different lineages because the crab form just makes a ton of sense. So I think a lot of these ideas, they kind of extrapolate naturally from the stuff that already exists. So being the first one to extrapolate is not necessarily that important. Today, the most popular RNN is the long short-term memory, the LSTM, which has become the most cited neural network of the 20th century. Okay. 1958, back to the atomic age here, and we have multi-layer feed-forward neural networks. We have this guy, Frank Rosenblatt, not only combined linear neural networks and threshold functions, he also had more interesting, deeper multi-layer perceptrons, MLPs, right? So now we're moving from just one layer of neurons to one layer of neurons with another layer of neurons immediately on top of it, and then however many, right? And that's what the word deep there means. It's how many layers of neurons you have. So it seems like this guy was the first guy to put a couple layers on top of each other's. His MLPs had a non-learning first layer with randomized weights and an adaptive output layer. Rosenblatt basically had what much later was rebranded as extreme learning machines. MLPs were discussed in 1961 by Steinbuch, Roger David Joseph, Oliver Selfridge. Okay, so you have a variety of people here towards the beginning of the 1960s starting to take all these original kind of neural network ideas and start kind of stacking them together. So like layers of neural networks is coming from the 1960s here. So Rosenblatt even wrote about backpropagating errors. So maybe he coined that term there. although he did not yet have a general deep learning algorithm for MLPs. What's now called backpropagation is quite different and was first published in 1970 as described below. Okay, so today the most popular feed-forward neural network is a version of the LSTM-based highway net called Resnet, which has become the most cited neural network of the 21st century. Resnet is a residual network, so you have the multiple layers of neurons, but then you also have neurons that not only connect to just the layer on top, the layer below, but they'll go around and they'll connect to neurons that are multiple layers ahead, right? These are called residual connections. Right. So I like this picture. So you see this red one here. Normally it would just connect to the green ones and then connect to the purple ones, but you can actually see that it'll connect all the way with the orange one in the back. So this is residual connections and ResNet. But again, I don't know, the most popular, I don't think that's correct. I would say the most popular neural network today is a transformer, not a ResNet. Okay, successful in deep learning feed-forward network architectures, 1965. Okay, so we're still kind of atomic age here. Is that actually what atomic age means? Like, what is the formal definition of atomic age? 1945. Is 1960s considered atomic age? Maybe not. 1950s, 1960s, 70s. Okay, yeah, I think that I'm okay with that terminology. I'm not a historian, but I just wanted to make sure. So in the USSR, specifically Ukraine, you have this guy, Alexei Ivaknenko, and this other guy, Valentin Lapa, introduced the first general working learning algorithms for deep multilayer perceptrons with arbitrarily many hidden layers. So in 1971, they had a deep learning net with 8 layers. That's a lot of layers now. So you have actual deep learning in the 60s. Especially in Eastern Europe, where much of machine learning was born. Okay, so I'm assuming he obviously was some kind of professor, and then kind of his brood of PhD students and graduate students were maybe some of the, what he's talking about here with Eastern Europe, where machine learning was born. Given a training set of input vectors with corresponding target output vectors, layers are incrementally grown and trained by regression analysis, then pruned with the help of a separate validation set where regularization is used to weed out superfluous units. Okay, so you have here the idea of pruning. So this is something that is very common in modern deep learning, but for a different reason. So people will train a neural network and then prune it, so get rid of the weights that are very small and don't really do anything. Like there's neurons that are just kind of like just very lightly activating and don't really do anything. You can just get rid of them, so you don't have to compute them, so that you can get a pretty good version of your neural network with basically half the amount of neurons. So that's kind of a version or a reason that people prune neural networks now, is to reduce the total amount of computation, which actually might be the reason they were doing it here as well. Like later deep neural networks, Ivaknenko's nets learned to create hierarchical distributed internal representations of incoming data. They do not call them deep learning neural networks, but that's what they were. In fact, the ancient term deep learning was first introduced much later by Dechter in 1986 and Eisenberg in 2000. Our 2005 paper on deep learning was the first machine learning publication with the word combination learn deep in the title. Okay, so we're coming out of the 1960s now, and we're kind of coming into the 70s, and you have Amari, who's, I think we already had a picture on this guy. Yeah, here he is. So here he is much older, and now I guess this is him when he's much younger. train their deep networks, and then you had Amari suggested to train the MLPs with many layers in non-incremental end-to-end fashion from scratch by stochastic gradient descent. Okay, so I think the key difference here is that if you look at what Ivaknenko was doing, he was incrementally growing the layers. So, right, you had a neural network with 8 layers. He would basically train the first layer, then he would add a second layer, then train the second layer, then he would add a third layer, then train the third layer. So Amari was kind of the first, I guess, here to suggest that, hey, just train all of them at the same time, use the chain rule to go all the way down through the network, and then use a stochastic gradient descent, which is actually not his original thing. It's from this Robinson Monroe. So Amari's implementation learned internal representations in a 5-layer MLP with 2 modifiable layers, which was trained to classify non-linearly separable pattern classes. Back then, compute was billions of times more expensive than today. Amari was also the first to publish learning neural networks in 1972. So a lot of stuff came out of this Amari guy. All right, so we officially are past the 1960s, and we're now into the 1970s and the 1980s. So 1970s, you now have this guy Seppo Linnainmaa. I don't know what that is. What is this guy's nationality? That's Finnish. Okay, I was gonna say, that's a weird ass name. Okay. First to publish what's known as backpropagation, algorithm for credit assignments in the network of differentiable nodes. I guess he called it reverse mode of automatic differentiation. It is now the foundation of widely used neural network software packages such as PyTorch and Google's TensorFlow. Where's JAX there? Gotta reference JAX. 1982, you now have this different guy, Paul Werbros, proposed to use the method to train neural networks and extending his ideas in the 1974 thesis. What? Oh, okay, so he originally proposed it in 1974, but then in 1982, he kept going with that. 1960, Henry J. Kelly already had a precursor of backpropagation in the field of control theory. This guy here, Kelly, very grainy, crappy picture. See also later work for the 1960s by Stuart Dreyfus and Arthur Bryson. Unlike Linnainmaa's general method, the system of the 1960s backpropagated derivative information through standard Jacobian matrix calculations from one stage to the previous one, neither addressing direct links across several stages nor potential additional efficiency gains due to network sparsity. Okay, so this part here, potential additional efficiency gains due to network sparsity, that's kind of what we were referring to here when we said that when you can prune a neural network and get rid of some of the neurons, basically zero them out, then it makes it easier to calculate things because you basically don't need to perform those calculations when you're doing these chain rules. And especially in these guys' era, right, the 70s and 60s, like you didn't have the type of computation. You had to be doing these things by hand, potentially even with punch cards. So every kind of multiplication that you can save yourself from doing is a huge speed advantage. Okay, backpropagation is essentially an efficient way of implementing Leibniz chain rule. So now we're starting to move into efficiency, right? Leibniz is back from our kind of ancient history. He just tells you chain rule where, hey, these two things, if you look at the infinitesimal change here, that relates to the infinitesimal change here in this way, right? Like kind of the fundamental idea of calculus. And then you have the chain rule, which is just relating basically derivatives with each other. But now in this era, they're trying to figure out how to do it faster. So Cauchy's gradient descent uses this to incrementally weaken certain neural network connections and strengthen others in the course of many trials, such that the neural network behaves more and more like some teacher which could be human, blah, blah, blah. Okay, so you're changing the network weights. So in 1985, compute had become about 1,000 times cheaper than 1970. So 1970 to 1985, you have a 1,000x compute improvement. And the first desktop computers had just become accessible in wealthier academic labs. Yeah, I think if you actually look at the history of, for example, Microsoft, I think this is right around, like, there's a bunch of, I think both Bill Gates and Steve Jobs were born right around this period, right? Like the 60s into the 70s. And one thing that they both had in common is that they were both born in an area where they had access to the kind of very first computers when they were young. So, again, computers had just become accessible in wealthier academics' labs. So a lot of times these kind of founder people that like kind of start something, it has to do with the fact that they're born in a very particular place that gives them access to a very particular new type of technology which nobody else has access to, so then they can become very good at that technology before anybody else gets access to it, right? I think that's the case with both Steve Jobs and Bill Gates. So backpropagation can yield useful internal representations. Backpropagation is generally more efficient than Amari's deep learning through the more general SGD method. Okay, it took 4 decades until the backpropagation method of 1970 got widely accepted as a training method for deep neural networks. Before 2010, many thought that the training of neural networks with many layers requires unsupervised pre-training. Schmidhuber says he introduced this in 1991. In fact, it was claimed that nobody in their right mind would ever suggest to apply backpropagation to deep neural networks. But in 2010, our team showed that deep, fully connected neural networks can be trained by plain backpropagation and do not at all require unsupervised pre-training for potential applications. Our system sets a new performance record on the back then famous and widely used image recognition benchmark called MNIST. This was achieved by greatly accelerating deep neural networks on highly parallel graphics processing units called GPUs, as was first done for shallow neural networks with a few layers by Jung and Oh in 2004. Yeah, so I think this is literally right here. This little side note in a parentheses is like the entire thing. Is that all of this neural networks approaches, they were kind of more like toy problems, right? And they were always limited by, you need to do so much computation, you need to multiply all these different numbers, you have to do all this training, and you have to backprop and multiply more numbers, and the chain rule just gets bigger and bigger and bigger the more layers you have, and it's never going to be anything more than a toy problem. But then in 2004, these guys, Jung and Oh, took a GPU and they were like, hey, we can actually probably use this GPU, which does a bunch of multiplies and adds and is quite good at that. And we can use it to train these neural networks, which are just a bunch of adds and multiplies. And then I think this here is literally these guys deserve kind of the most credit for the modern deep learning, because they actually went ahead and started using GPUs, which I think is literally the most important part. Unfortunately, several authors who republished backpropagation in the 1980s did not cite the prior art, not even in later surveys. In fact, as mentioned in the introduction, there's a broader, frequently repeated misleading history of deep learning which ignores most of the pioneering work, blah, blah, blah. Okay, this is like just him ranting about like not receiving proper attribution. And let's come up to here. So 1979, the first deep convolutional neural networks, and in 1969, ReLUs, recurrent linear units, which is the activation function. That's very common. Computer vision was revolutionized in the 2010s by a particular feed-forward neural network called the convolutional neural network. The basic CNN architecture with alternating convolutional and downsampling layers is due to Kunihiko Fukushima, this guy right here, he called it neocognitron. What a badass name, right? We should have just kept that name, neocognitron. Remarkably, already 10 years earlier, Fukushima introduced rectified linear units for neural networks in 1969. They're now widely used. There are more, I wonder how you can do that. Most common activation functions 2022. Like, I wonder if you could like somehow like scrape GitHub and get this information. Sigmoid, TANH, ReLU, leaky ReLU. So this one here is the ReLU, this yellow one. And one of the big reasons people use it is actually because it's very simple. It's just flat and then linear, so it's like piecewise. So very easy to compute and represent in a computer. These other ones here, the TANH and the sigmoid, these like curves, they're more annoying to compute. There's another one that people use a lot that's called the GeLU. Yeah, this is the one that I think is more popular now. It's basically like a ReLU, but it has this little dip here. Okay. So 1987, neural networks with convolutions were combined by Alex Weibel with weight sharing and BackPropagation and applied to speech. A popular downsampling variant called max pooling was introduced by Yamaguchi in 1990 and Zhuan Wang for high-dimensional CNNs in 1993. So I think the late 80s, early 90s, you can see that people are already playing with very kind of advanced versions of this, right? They have CNNs, they have rectified linear units. They're not quite training them with GPUs yet, but they're doing stuff. They're doing like speech, right? Speech classification. I think this is the beginning of MNIST, probably. Yeah, Jan LeCun's going to come in here. Here we go, Jan LeCun. Baldi and Chauvin. 1993. We're already doing CNNs on biomedical images. Our fast GPU-based CNN of 2011, known as DANnet, was a practical breakthrough much deeper and faster than earlier GPU-accelerated CNNs of 2006. In 2011, DANnet became the first pure deep CNN to win computer vision contests. Yeah, so this is interesting. I did not know that. To me, like I'd always thought ImageNet, or in the ImageNet challenge, the AlexNet, this one here, this to me was kind of the quote-unquote beginning of neural networks being trained on GPUs, and then kind of everything goes from there. But I mean, if Schmidhuber's right, he did have the first version of that, right? He, in 2011, in whatever this is, IGCNN 2011, DANnet was really the first one there. So, damn, leave it up to Schmidhuber to tell you that he actually had AlexNet before AlexNet. DANnet enjoyed a monopoly from 2011 to 2012. It won every contest it entered. DANnet blew away the competition, achieved the first superhuman visual pattern recognition. DANnet was also the first CNN to win a Chinese handwriting contest, image segmentation contest, and object detection in larger images, and a medical imaging contest on cancer detection. CVPR paper on DANnet hit the computer vision community. 5 months later, the similar GPU-accelerated AlexNet won ImageNet. Yeah, so there you go, man. I mean, he's not wrong. You know, he's saying that they published it in 2012, and then whoever, Alex Shchevsky or whatever his name is, I don't know his last name, it's some Russian thing. But 5 months after that, he was like, hey, I can do that. And he did another GPU-accelerated convolutional neural net known as AlexNet, and then he won the ImageNet. Okay. This attracted tremendous interest from the healthcare industry. IBM, Siemens, Google, and many startups are pursuing this approach. Resnet, the ImageNet 2015 winner, is a version of the earlier HighwayNet. And the HighwayNet is actually a feed-forward net version of our vanilla LSTM with hundreds of layers. CNN is also not a great news network. But is it convolutional? Deep learning architectures that can manipulate structured data, such as graphs, were proposed in 1987 by Pollock. Okay, so he's kind of going back and forth in time here. I think he traced out the kind of convnets. Now he's tracing out graph neural networks here, which also have kind of a similar kind of time period of innovation here in the like kind of late 80s, early 90s. Again, a bunch of kind of German people here, Eastern European, maybe. Self-organizing maps, various proposals of biologically more plausible deep learning algorithms. The stochastic delta rule in 1990. Decades later, a version of this became popular under the moniker dropout. Yeah, so stochastic here refers to randomness, right? And in dropout, during training, you'll randomly basically zero out some of the neurons, and then by doing this randomly throughout training, your network becomes more resilient, better, because it forces the representation to kind of flow through the remaining neurons. So there you go. Dropout, originally invented in 1990, although I'm sure the original idea is older. We mostly limit ourselves to the, in hindsight, most essential ones. Okay. February 1990, generative adversarial networks and curiosity. Generative adversarial networks have become very popular. They were the first published in 1990 in Munich under the moniker artificial curiosity. Huh. Okay, so I thought Gans was an original idea by Ian Goodfellow, and he has a story about it, like talking with his friends in a bar and then like running back home and writing it. So Schmidhuber says that's not the case, and that they've been there since the 1990s. Dueling neural networks, that's kind of a cool way to talk about Gans, because in Gans, right, you have a generator and a discriminator. Here, the generator, called the controller, generates outputs, and then the predictor, or in this case discriminator, sees the outputs of the controller and predicts environmental reactions to them. So you have two neural networks kind of training each other. And that's actually what makes them hard to train Gans, is that if either the generator or the discriminator kind of becomes better than the other one, then the training collapses. They're not very popular anymore, to be honest. Diffusion models are more popular. The predictor neural net minimizes its error, while the generator tries to make outputs that maximize this error. 4 years before a 2014 paper called GAN, my well-known 2010 survey summarized the generative adversarial neural networks as follows. A neural network as a predictive world model is utilized to maximize the controller's intrinsic reward, which is proportional to the model's prediction errors. So Schmidhuber really wants the credit for Gans here, is basically what he's saying. In 2014, Gans are a instance of this where the trials are very short, and the environment simply returns 1 or 0 depending on whether the controller or generator's output is in a given set. Other generative adversarial were very different. They neither involved unsupervised neural networks nor were about modeling data. Okay, predictability, minimization, and artificial curiosity. Jürgen Schmidhuber, this might be like, I don't know, some picture that he had for some paper. 1990 principle is widely used for exploration and reinforcement learning for synthesis of real images. Ah, here you go. He does say that even though Gans were popular for a little bit, little flash in the pan moment, they have been replaced by diffusion models. Which I guess he's also saying he's also created a fusion model or diffusion models. Man, this guy, he thought of everything. He wrote it all down, and now everything comes from his notebook, I suppose. I published yet another ML method based on two adversarial networks called predictability minimization for creating disentangled representations of partially redundant data. Okay, 1990. Neural networks generate sub-goals and work on command. Most neural networks of recent centuries were dedicated to simple pattern recognition and not to high-level reasoning, which now considered a remaining grand challenge. I mean, I would say that one thing that we've learned, especially with these large language models, is that the high-level reasoning, you don't need to, I don't think you need to encode that, right? I think the same mistake that we made thinking that you need feature engineering, and then it turns out you don't. If you just make a neural network and you make it deep enough and you train it on a big enough data set, the features that it gives you are better than the features that you hand engineer. I think high-level reasoning is the same thing, is that we think that high-level reasoning requires some kind of heuristic and some kind of human-designed architecture, but it doesn't. I think eventually they're just going to keep making the large language models bigger and bigger and bigger, and you can see it just predicting the next token in a sentence is enough of a learning objective that these language models learn all kinds of super high level abstractions and like kind of the early forms of reasoning. So I think we're just waiting for scale, but it'll come with what we already have. Neural networks that learn to decompose complex spatio-temporal observation sequences into compact but meaningful chunks. This work injected concepts of traditional symbolic hierarchical AI into end-to-end differentiable subsymbolic neural networks. Hierarchical reinforcement learning. So reinforcement learning, but you have different hierarchies of learning systems. So you might have neural networks at the like kind of lower level, and then you have kind of human logic at the top. Although you can do it with neural networks all the way up and down, right? Soon afterwards, this was done with recurrent neural networks. A neural machine gets extra command inputs of the form start and goal, and then you have a neural network that learns to predict the current reward and cost of going from start to goal. So this is the beginnings of the Markov decision problem here, where you have this idea of starting, you have this idea of end, you have this idea of actions, right? Command inputs or action space. You have rewards and costs. So these are all kind of the basic pillars of reinforcement learning here. And you put a neural network there that tries to learn the action that maximizes the reward, the expected reward over a whole episode, where an episode is basically from the start to the end. Here they're calling it goal. Other neural networks that have worked on command since 1990, in particular learning selective attention, artificial curiosity in self-inverted problems. Upside-down reinforcement learning. What is upside-down reinforcement learning? And its generalizations. Recently, transformers. All right, here we go. Who was the first person to come up with transformers? Tell me. Recently, transformers have been all the rage, e.g. generating human-sounding text. This is LLMs. Transformers with linearized self-attention were first published in 1991. Okay. These so-called fast-weight programmers or fast-weight controllers separated storage and control like in traditional computers, but in an end-to-end differentiable, adaptive, fully neural way. The self-attention in standard transformers combines this with a projection and softmax. Okay, so basically the self-attention mechanism of transformers, which I guess is, does he have the Transformers paper? 2010s, originally comes from a 1991 paper here called Fast Weight Controllers. Okay, so he has a picture here. You have the key, value, and query part. These are kind of basic parts in a transformer attention mechanism. Neural networks learn to program neural nets with fast weights. The outer product version is a linear transformer. Slow, fast. Okay, so I suppose if you follow the dotted lines here, the connection pattern of this neural network here is actually the same thing as a transformer. Today's transformers heavily use unsupervised pre-training, right? So masked language prediction is a form of unsupervised pre-training that's very popular. So predicting the next token, taking a sentence and filling in the missing word. And the reason these unsupervised pre-training methods have kind of become standard is because if you have a very large data set, you don't want to have to put that into like a input and target kind of format, which is what you would use in like a supervised learning for like image classification. So unsupervised pre-training has exploded because of the availability of extremely large data sets that aren't necessarily in the best format to do kind of supervised training. Fast weight programmers also led to meta-learning that can run their own weight change algorithm or learning algorithm themselves. This work since 1992 extended his thesis, blah, blah, blah. Learning to learn. Yeah, meta-learning is something that I've also seen. There's a robotics researcher, Chelsea Finn, who was there at Google when I was there, and she was like the king of meta-learning. And there was a bunch of different papers, I think model agnostic meta-learning, yeah. So basically the idea here is that this is the weights of a neural network here. Actually, here we go, with pictures is better. And you put the weights of that neural network theta such that you can very quickly fine-tune it to a different task. Right, so you have kind of a learning loop that tries to move the initial weights of the neural net in such a way that it becomes better at generalizing to other tasks and being able to be fine-tuned. So, I don't know, in my kind of primitive lexicology, I would think that it's a form of kind of hierarchical learning, right? You have like a loop, a training loop within a larger training loop within potentially even a larger training loop. But meta-learning is the actual term for that. Token prediction is main computation. Yes. Yes, most LLMs are just doing token prediction. Yeah, the Transformers toy line came out. We should give credit to the Transformers toy line for coming up with the word transformer. Is that actually, what is the origin? Transformer, what is it called? Etymology? Like where does that even come from? Vocabulary.com. Transformer comes from 1600. One who or that which transforms. Okay, well, where does transform come from? Transform comes from the Old French transformer, which comes from Latin transformare, which comes from trans, which is across and beyond, like transhumanism, and then formare, which is to form. So it's originally Latin, so that's where all the attribution should go, to the Old French Latin person. 1772. Okay. 1991. We're getting there. This is a very long article, but we're almost there. We got a little bit more. Maybe a lot more. Maybe we should be faster. Right, deep learning and self-supervised pre-training, 1991. Most powerful neural networks tend to be very deep. That is, they have very many layers of neurons or many subsequent computational stages. For the 1990s, gradient-based training did not work very well. For deeps, only shallow ones. Again, you have this kind of exploding and vanishing gradient problems. Recurrent neural networks, or not recurrent, residual neural networks have feedback connections. This makes RNNs powerful process inputs. RNNs can, in principle, implement any program that can run on a laptop or any other computer in existence. This is like the Turing completeness of neural networks. RNNs can, in principle, deal with problems of arbitrary depth. Yeah, I don't think the like theoretical guarantees of like Turing completeness mean anything, you know. Built a self-supervised RNN hierarchy that learns representations at multiple levels of abstraction and multiple self-organizing timescales, called the neural sequence chunker, or neural history compression. Although computers back then were about 1 million times slower per dollar than today, by 1993, the neural history compressor was able to solve the previously unsolvable very deep learning tasks with depths of greater than 1,000. Okay. More than a decade after this work, FNNs was published, feed-forward neural networks, facilitating supervised learning by unsupervised pre-training of stacks, called deep belief networks, DBNs. Each higher level tries to reduce the description length or negative log probability of data representation of the level below. The internal representation can be collapsed into a single recurrent neural network. Yeah, so this is like kind of, ooh, I clicked on something. This is the student-teacher kind of paradigm that you see sometimes, where you have kind of a teacher neural network and a student neural network, and the student neural network just learns to imitate the teacher, and usually the student will be a smaller, shallower network, and that's kind of another form of computation improvement. In this case, you're going to spend more time training it because you're going to have to train the teacher and then you're going to have to train the student. But if you have to run a neural network on like a very small embedded device or something where inference speed matters, you can do this kind of distillation with this teacher-student training. So Schmidhuber says he was doing this in 1991. Unsupervised pre-training is heavily used by transformers for natural language processing. Okay. Transformers with linearized self-attention were also first published in 1991. Okay, so he's also the Transformers guy. You heard it here. He was, not only is he the GPU guy, he's also the recurrent neural network guy, and he's also the GAN guy, and he's also the Transformers guy. I don't think he would lie in this paper. Like, that seems to me very dishonest. I don't think he would lie. So I feel like he's saying the truth here, but I don't know. If he's saying the truth, then he's not wrong, and he's been getting gypped for all of this. He's really the founding member of everything. Deep learning, identified and analyzed Sepp Hochreiter in his diploma thesis. He showed that deep neural networks suffer from the now famous problem of vanishing or exploding gradients, which is that in typical deep or recurrent networks, backpropagated error signals either shrink rapidly or grow out of bounds. In both cases, learning fails, and this analysis led to basic principles of what is now called a LSTM. LSTM, or the long short-term memory recurrent neural network. The 1991 diploma, which Schmidhuber considers one of the most important documents in the history of machine learning. Okay. Swiss LSTM grants. A milestone was the vanilla LSTM architecture with a forget gate. So LSTM, right, long short term, there's a picture of this. Yeah, this is what it is. So you have x of t as the input, and then one of these gates here is a forget gate, and what it does is it basically zeroes out certain parts of the previous state. So basically you have the input x of t, and then there's some output h of t, but then the output from the previous time you performed inference is here. So this is like the whole time-based thing I was talking about, even though I'm doing a terrible kind of explanation of it, but like here maybe is a better one. So these are different inputs, usually in time, and this is the outputs, right? So for each input in time, you're going to have some output in time. But the neural network here, the LSTM that is taking your current input in time and eventually giving you your output in time, is also outputting this like hidden state, right? And that hidden state gets fed into the next one. So that means that this neural network here not only does it know what the current input is, but it also knows what the previous hidden state was. And the forget gates are basically just a little gate or a little mathematical term within the LSTM that basically, where is it here? TANH, maybe it's this one. But it basically allows certain parts of the context from the previous step, right, that hidden state, to be kind of zeroed out. So that's the forgetting. It's saying, hey, this part from the previous step, I don't want to use this going forward, so I'm just going to zero that out. Alex was lead author of our first successful application of LSTM to speech. And you have bidirectional LSTM, which is LSTM that kind of works both ways in a sequence. Another milestone of 2006 was the training method connectionist temporal classification, or CTC. I've never heard of that. I don't know what that is. This led to superior neural network speech recognition. Okay. Hidden Markov model. So this is Markov model. You could basically, that's the core part of reinforcement learning, right? With the state, action, reward, and so on. Hidden Markov model is where you don't actually know what the state is. And there's another variant called partially observable Markov models. So there's POMDPs and so on. 3 ICD-AR handwriting competitions, and then I guess they performed well in those in 2015. Google's on-device speech recognition of 2019, now on your phone, is still based on LSTMs. All right, 1995, neural probabilistic language models. Okay, LSTMs can learn languages unlearnable by traditional models such as HNMs. By 2016, Google Translate, whose white paper mentions LSTM over 50 times, was based on 2 connected LSTMs, one for the incoming text and one for the outgoing translations. By 2017, LSTM also powered Facebook's machine translation, Apple's QuickType, Amazon Alexa, Google's image caption generation. By 2016, more than a quarter of the awesome computational power for inferences in Google's data sensors was used for LSTMs. So yeah, LSTMs were very popular in kind of the late 2010s because they actually worked quite well. Through the work of my students Rupesh Kumar Srivastava and Klaus Graf, the LSTM also led to the highway network, which I think is the one that they said led to Resnet, yeah, which led to Resnet, and then the ImageNet and AlexNet and so on. Microsoft's Resnet is a version thereof. The earlier highway nets perform roughly as well as their Resnet versions on ImageNet. So deep learning is all about neural network depth. I would say that it's more about the size of the data set, but the size of your neural network is also important. LSTMs brought essentially unlimited depth. LSTMs has become the most cited neural network of the 20th century. I would say, I don't know about that, I would say the attention is all you need paper, given that the release of machine learning papers is accelerating and there's more and more papers every year, I would say that the transformer attention is all you need paper is going to supersede that very quickly, and that's going to become the go-to, or the most referenced paper. Citations, however, are a highly questionable measure of true impact. Could be necessarily true. Okay, 2010s. Or 1980, sorry. Learning to act without a teacher. Neural networks are also relevant for reinforcement learning. Yes. RL agents must discover, without the aid of a teacher, how to interact with a dynamic, initially unknown, partially observable environment in order to maximize their expected cumulative reward signals. It's a nice little summary of RL there. There may be arbitrary, a priori unknown delays between actions and perceivable consequences, right? This is kind of a problem with RL where basically like the reward is not going to be a very good signal, right? Like within an environment, you might only get reward at the very end, which makes it very difficult to backpropagate that reward signal to actions that happen much earlier. And part of the way that people have solved this is that they do what's called reward engineering or reward shaping, where basically they spend a lot of time crafting very elaborate reward functions that allow the reinforcement learning model, the neural net that's actually doing that and trying to learn the reward, that allow it to kind of more easily map specific actions that were taken to reward. Certain RL problems can be addressed through non-neural techniques, Monte Carlo tree search, dynamic programming, artificial evolution, alpha-beta pruning, control theory, and system identification, stochastic gradient descent, and universal search techniques. So that's a nice little summary of all the different ways to not use neural networks to do reinforcement learning. Deep fully connected neural networks and recurrent neural networks, however, are useful tools for improving certain types of RL. Function approximation and system identification, TD learning. So this is the actual loss function that reinforcement learning uses, temporal difference learning. A class of model-free reinforcement learning methods which learn by bootstrapping from the current estimate of a value function. So you're using a neural network to estimate a value function, right, which is a function that estimates the value of a current state, which is kind of a proxy for the reward that you would receive in that current state. So you have different neural networks here. You have one that's actually performing the actions and figuring out what action to take at a certain state, and then you have a value function, which is determining what the value of a current state is. When there is a Markovian inference to the environment such that the current input to the RL machine conveys all the information required. RL with dynamic programming, temporal difference, or Monte Carlo-based FNNs can be successful, as shown in 1994, where you had master-level backgammon, and then in the 2010s when you had Go, chess, and I think here this is the OpenAI Dota. I still think there's a lot of problems with Markov formulation for reinforcement learning. I think there's a reason that they only work in these games like Go and chess and even Dota, because these games are they're perfectly predictable. You know, it's like if you're in the same state and you take the action, you'll end up in the same state. It's like, especially a game like chess or Go, where like there's no fuzziness, right? It's like a discretized world. The whole world is just discretized, and then once the world is discretized, then you can learn these value functions, you can learn these neural network agents that can actually do stuff. But I think the real world is too analog. There's too much fuzziness, and like there's no such thing as a state. You know, like there's an infinitely many states that you could be in, and there's infinitely many actions. So like once you explode the state in the state space and the action space, then these approaches don't work. It would take infinitely long to explore that space. One way to potentially solve that is make better and better and better simulators, right? And then just kind of brute force with compute. Or maybe there's a different formulation here that could be used. I think like some playing with the ideas of kind of curiosity-based learning and like maybe other types of more unsupervised reinforcement learning style stuff, rather than this kind of like make a reward function, shape that reward function, and learn a value function, then go from there. Okay, OpenAI's famous Dactyl, which learned to control a dexterous robotic hand. In DeepMind, co-founded by a student from my lab. Okay, so interesting. One of the DeepMind co-founders. I wonder if that's Hassabis. This dude. This is the DeepMind guy. This guy's pretty badass. No, I don't think. Maybe it's the other guy. Who's the other founder? Shane Legg and Mustafa Suleiman. Maybe it's this guy? I don't know. One of those two guys is Schmidhuber's student. Bill Gates called this a huge milestone in advancing artificial intelligence. Random opinion of the day goes to Bill Gates right there. Future of RL will be about learning, composing, planning with compact spatiotemporal abstractions of complex input streams. I would disagree with the compact spatiotemporal abstractions. I think compacting them and discretizing them is part of the problem. And learning to think. how NNs can learn to represent percepts and action plans with a hierarchical manner at multiple levels of abstractions. We published answers to these questions in 1991. Apparently, in 1991, Schmidhuber was zooming. He was just doing everything, discovering everything. He wrote down all of it. This year was the most fruitful year in the entirety of theoretical neural network world. Learn hierarchical action plans. Okay. Let's see. Broader historical concepts. Okay, we're almost there, guys. We're sprinting to the end here. I think this is probably the most important section here, though, which is actually the computation. It's the hardware. I actually agree with this. Like, some of these earlier opinions, I think he's being a little bit pompous and saying that he's the originator, but I do... Actually, I should probably read this section, but I think I'm 100% a believer in that the theoretical advancements and ideas behind neural networks and deep learning are actually kind of bogus, and like 99.9% of it is just the computation speed and improvement over time. It's basically Moore's law. So recent breakthroughs of deep learning from the past millennium would have been impossible without continually improving and accelerating computer hardware. The history of AI and deep learning would be incomplete without mentioning this evolution, which has been running for at least 2 millennia. First known gear-based computational device was the Antikythera mechanism. Yeah, this is a crazy one. It's like this mechanism they found in the bottom of the Mediterranean in a boat wreck, a shipwreck. And it was basically this little bronze like wheel that like basically would point and tell you the different eclipses. Antikythera mechanism. Yeah, there's like a GIF of it that I think is really cool. But yeah, this is what it looked like, right? So just imagine living in like ancient Greece and like you're sitting here and like some guy brings you this like copper like box that like has all these like gears, and it like kind of predicts, and it tells you can just like put in where the current space of the Earth is, and it'll kind of like calculate, and using all these little gears tell you what the I don't know what it tells you, maybe what the moon is or something like that. But very, very cool stuff. Perhaps the world's first programmable machine was an automatic theater machine made by Heron of Alexandria, who had also made the first steam engine. Programmable automaton by Heron. And in the 9th century, music automation by Banu Musa brothers in Baghdad was perhaps the first machine with a stored program. Okay, so you had a rotating cylinder, and then this cylinder had little like kind of dots or bumps on it, right? And one of those things that you kind of turn, and then it controlled a steam-driven flute. So this idea of kind of like storing data and then using that to like move a mechanism in a repeatable way goes back very, very old, but you can see here a bunch of different versions of it. Okay, and then 1600, so you kind of go through the dark ages of like the first 1,000 years after the BC, right? First 1,000 or AD, first 1,000 years AD, and then you get to the Renaissance area here, Renaissance period, 1600s. Brought more flexible machines that computed answers in response to input data. The first data processing gear-based special purpose calculator for simple arithmetics was built in 1623 by Wilhelm Schickard, one of the candidates for the father of automatic computing. Yeah, so this is like 50 years before this Leibniz guy who we saw was the guy who did calculus and the chain rule. Designed the first machine that could perform all 4 arithmetic operations and the first with a memory. He also described the principles of binary computers governed by punch cards, 1679, and published a train rule. The first commercial program-controlled machines, punch card looms. So a loom is like what they use to make textiles, right? It's like this big giant machine that basically makes those like little cross patterns that are the fundamental backbone of clothing. And a punch card is basically like I mean, it's changed. It used to be, if it was paper, but I'm sure before it was actually made out of wood or like metal or something like that. And it has holes in it, and those holes, right, will cause like a little thing to dip into the hole, and that dipping causes the rest of the machine to do something. Planned, but it was unable to build a programmable general purpose computer. Okay. The Spaniard Leonardo Torres y Quevedo, mentioned in the introduction, became the 20th century's first AI pioneer when he built the first working chess endgame player in 1914. Back then, chess was considered an activity restricted to the realms of intelligent creatures. Okay, the machine was still considered impressive decades later. Between 1935 and 1941, Konrad Zuse created the world's first working programmable general-purpose computer. So early 1940s. Described the digital circuits required by programmable physical hardware, predating Claude Shannon's 1937 thesis on digital circuit design. Okay, so interesting. Shannon, famous from Shannon entropy. This is kind of a famous computer scientist, but it seems like his digital circuit ideas was actually not original, and it came from this other guy, Konrad Zuse. Unlike Babbage, Zuse used Leibniz's principle of binary computation instead of traditional decimal computation. Okay, so I think this is analog versus digital circuitry here, right? It's like basically, are you dealing with only zeros and ones, or are you dealing with kind of something that can vary between kind of 0 and 1, like infinite float precision or binary 0 1s? Physical hardware was indeed universal and purely theoretical but impractical. Okay. Simple arithmetic tricks can compensate for Z3's lack of explicit. Why does he keep calling him Z3? Oh, it's the computer, the Z3. Okay. Lack of an explicit conditional jump instruction. Today, most computers are binary like the Z3. That's cool. I think there are a bunch of startups that are trying to do like non-binary computers. They're like light computers. I've seen this before, where it's like kind of it uses light, which is itself not binary, right? It's a kind of can vary. It's like an infinite precision. C3 used electromagnetic relays with visibly moving switches. First electronic special purpose calculator was the binary ABC made in 1942 by this guy, John Atansoff, the father of tube-based computing. So instead of kind of gear-based machines and these little punch cards, he used vacuum tubes. This is like old steampunk technology here. Today's machines use the transistor instead of vacuum tubes, so you go from kind of gears to kind of mechanical punch card type things to tubes, vacuum tubes, and then finally to transistors, which is what we use now. Yeah, and then one of the very famous early computers was the one that was used to break the Nazi code. And I think there's a movie with Benedict Cumberbatch about that, the Enigma, I think it's called. Abacus was the first computational storage device. Yeah, I mean, who deserves credit for the abacus invention? You know? Schmidhuber, there's a Schmidhuber paper of 3000 BC where he invents the abacus. Zeus, blah, blah, blah. Both data and programs were stored in electronic memory by the Manchester Baby. I guess that's another computer. Computers have become much faster through integrated circuits. In 1949, this guy at Siemens filed a patent for an integrated circuit semiconductor with several transistors on a common substrate. Some other guy demonstrated integrated circuit with external wires. Then monolithic integrated circuits. And then 1970s, I guess, is when you have the first GPUs. That's cool. I mean, I'd be curious, like, when is the first GPU? Is that what he's saying, 1970? Zeus's C3 could perform roughly one elementary operation, aka an addition per second. So one addition per second in 1941 is where we were at with compute. And I think that's probably the first data point for Moore's law. And now, 80 years after, computers can execute 10 million billion instructions per second in one. So yeah, you're talking, that's huge. It's a billion X more. The naive extrapolation of this trend predicts that the 21st century will see cheap computers with 1,000 times the raw computational power of all brains combined. Yeah, I think there's some people that are saying that Moore's law is dead and that we can't actually continue to get the same improvements over time. But I think that the general idea that compute is going to get faster and better is always going to be true. I think as long, like for the entirety of our lives, we'll continue to get more compute for cheaper. Technically, he is wrong. Currently, MOSFETs, a voltage control device, is the current technology in ICs. A transistor is a current control device. Also, the MOSFET is considered the most manufactured device in human history. That's kind of cool. Thank you, M9, for that fact. I am not an ECE. I don't know. Despite working in kind of technology, I'm not very good at kind of integrated circuits and printed circuit boards and all that kind of crap, so that's cool to know. MOSFETs is, I want to say op amp. Is that what that is? Or is that a different thing? This looks like different things. 1925. No. It's not the same thing. Okay. I'll stop embarrassing myself here. But back to it. Physics seems to dictate that the future efficient computational hardware will have a brain-like with many compact place processors in a three-dimensional space. Okay. Basic architecture is essentially the one of a deep, sparsely connected three-dimensional RNN. Op amps use MOSFETs. Okay. All right. My knowledge wasn't complete crap. I knew that somehow my brain was like, the word MOSFET is somehow strongly related to the op amp word in my head. That little... In the attention mechanism of my brain, the weight for that one was particularly high, even though I don't actually understand what either of those is, so. All right, don't neglect the theory of AI since 1931. Okay, second to last section here, let's go. Core of modern AI and deep learning is based on the simple math of recent centuries. To efficiently implement this core on the modern hardware and roll it out for billions of people, lots of software engineering was necessary based on lots of smart algorithms, blah, blah, blah. There is no room here to mention them at all. I'll list some important highlights for the theory of AI and computer science in general. Okay. So in the 1930s, Gödel, this is the Gödel incompleteness theorem guy, very smart mathematician dude. Lots of theoretical work based on integers and allows them for formalizing the operations of any digital computer in axiomatic form. Gödel used it to represent both data and programs. He famously constructed formal statements that talk about the computation of other formal statements, especially self-referential statements which imply that they are not decidable given a computational theorem prover that systematically enumerates all possible theorems from an innumerable set of axioms. Yeah, so here you have the P equals NP problem, which is, I think, quantum computers solve that. Godel built on earlier work. In 1981, George Cantor showed that there are different types of infinities. They can compare voltages, output a high or low. Oh, cool. These authors in turn built the formal algebra of thought, also by Leibniz. Dude, this guy keeps being relevant here. Alonso Church derived a corollary extension of Gödel's result by demonstrating that Hilbert and Ackermann Entscheidungsproblem, decision problems, does not have a general solution. So Ackermann steering in Hilbert space, this is these guys are also known for other things, especially in robotics. Okay, so you have one of the OG programming languages here, Lisp. And then the Turing machine introduced by Turing. I think in my primitive mind, I think these kind of things, the Turing machine, the like Gödel incompleteness theorem, like the Markov decision problem, like a lot of what I find wrong with these things is that they kind of discretize time, right? It's like they basically break, like the fundamental core assumption of everything here is that you can say a statement, that statement is true for some frozen state in time, and then you can change something. So it's like, it's basically reduces the world to a graph of like nodes and then edges that lead to other nodes and then edges that lead to other nodes. And then all of these theorems here are based around that idea. And it's just, the reason it's like that is because when you write things down, you like write it down and then there's like a point at which you say this is one complete equation or like this is one complete statement. And then you can write a different thing, but at that point it's a different complete statement. It's like there's this kind of fundamental discretization to human logic that kind of like forces all of these theoretical intuitions in that kind of like discretized human logic, like one thing after the other, step by step by step by step. But I think the reality is that the world is like kind of much more analog, kind of like everything happening at the same time. It's like, right, this idea of like all particles are simultaneously waves and particles, right? And I think that to me, this kind of thinking is like very particle based, of like there's a ball and then it hits into something and then it bounces off that thing. When in reality, everything is kind of more of a wave, and it's like kind of in a superposition of all possible states. I feel like that doesn't make any sense, that the rant I just went on, but it's like, it's this idea I'm trying to like kind of figure out a better way of like saying it in English, that a lot of human logic is based on this like kind of faulty core assumption that there's kind of a discretized nature to reality that is only true because there's a discretized nature to human logic and human speech. Much of early AI was actually about theorem proving and deduction in Gödel style through expert systems and logical programming. Ray Solomonov combined Bayesian probabilistic reasoning and theoretical computer science to derive a mathematically optimal way of learning to predict future data from past observation. And then you have this guy coming up with Kolmogorov complexity or algorithmic information theory. And this is a formalization of the concepts of Occam's razor, which favor the simplest explanation of a given data through the concept of the shortest program computing that data. There are many computable time-bounded versions of this concept. Okay, now you have Hutter in the 2000s, who basically applied this idea to reinforcement learning agents. Solving the problem as quickly, fastest solver. Even more general optimality of the Gödel machine. Practical modern AI is based on suboptimal, limited, yet not extremely well understood techniques such as neural networks and deep learning. Yeah, so I mean, this is important to know, is that there's nothing optimal about the training process that we currently use to train these neural networks, right? It's like you're performing stochastic gradient descent, right? The marble rolling on a hill analogy of like what you're doing is you're changing these weights in this neural net and you're like making these little marbles roll around this hill. The marble doesn't optimally move towards the global minimum of the hill, right? It doesn't know where that is. It just kind of like you're constantly kind of moving and you're going back and forth and back and forth, and like you're spending a lot of time updating weights in a suboptimal way, but like over time you keep doing that over and over and over again, and then kind of the average of all of those little tiny gradient steps actually puts you in a much better place than you were before. But it's interesting that so much time and effort was spent in like kind of the early 1900s thinking about like optimal computing and like what is the most efficient way to like execute this algorithm and like building a whole theory around that, when now so much of the compute that we perform when training these neural networks is basically noise, right? It's like you're just doing all this compute and like most of it is actually kind of not needed. But if you do that for long enough and with a big enough data set and a big enough network, it actually performs way better. Credit assignment. It's about finding patterns in historical data and figuring out how certain events were enabled by previous events. Okay. Historians do it, physicists do it, AIs do it too. All time since the Big Bang. Okay, so he has a cool little graph here. History seems to converge in an omega point in the year 2040 or so. Okay, so he's maybe kind of like a Ray Kurzweil fan here, and he believes in kind of this singularity point. Also, omega sounds much better than singularity. Okay, so he was the king of transformers. He's the king of GPUs. He's the originator of AlexNet. He's the originator of Resnets and LSTMs, and he's also the original singularity person. So Ray Kurzweil, back the fuck up, because Schmidhuber came up with that beforehand, I suppose. Let's start with the Big Bang 13 million years ago. We divide this by 4 to obtain 3 billion years. Okay, omega is 2040. Life emerged on this planet. So he has this symbol omega to be his singularity point, and then he says, if you actually calculate it out, it's omega minus 2, minus 9, minus 3, 13, and blah, blah, blah. So then basically you have 50 years, you have 1990, then minus 200 years, 800 years, 3,000 years, 13,000 years, 50,000 years, and so on. So if you do this, basically what it looks like is first life on Mars, first animals, first mammals, first primates, first hominids, first stone tools, controlled fire, anatomically modern humans, behaviorally modern humans, Neolithic revolution and civilization around 13,000 years, 3,000 years, Iron Age, 800 years, guns and rockets. That seems like kind of a really arbitrary thing. 200 years industrial revolution, 50 years information revolution, 13 years he's predicting cheap AIs with human brain power, and then by the time you get to 2040 You know, a lot of people actually say that the 2040, it used to be 2042, I think in Ray Kurzweil's book, but it's actually going to come sooner than we think. I think by 2030, we'll have more than human level AI, right? Like we're in the early 2020s and we already have basically, I would say ChatGPT is smarter than a lot of people, you know, like it definitely knows the breadth. It might not have like very complicated reasoning and like you can definitely confuse it, but to the people who say that you can confuse ChatGPT and it doesn't really know what it's talking about, I'm saying, hey, go to like some average place and talk to a person there, and then you'll very quickly realize that actually ChatGPT is probably beyond your average human being. So I think if that's what we have in 2022, by 2030, we're going to have very, very cheap AIs that you can just pay via an API that are significantly smarter than every single human, right? And then what does the world look like when it's 2040 and you've now had superhuman intelligences for 10 years, right? Because I think the superhuman intelligences will first be used in kind of limited applications, but then over time, they'll kind of trickle down, and every single possible job that could be done by them will be done by them. So what are humans doing in 2040? I don't really know. Okay, so we divide again by 4, blah, blah, blah. Okay, so this is going here. Germ theory of disease. Omega minus 50 years. Cheap personal computers. The European Particle Collider. Robot cars. All right, I want to see what he's predicting, though. Omega minus 13 years. That's a point in the near future, more or less the year 2030, where many predict that cheap AIs will have human brain power. Then the year 13, final 13 years until Omega, when incredible things will happen. Time won't stop with Omega. Maybe it's just human-dominated history that will end. Many curious meta-learning AIs that invent their own goals will quickly improve themselves, restricted only by the fundamental limits of computation and physics. Yeah, I think that this is kind of what I was talking about before. I feel like curiosity as a reward metric is the way that you get very, very good reinforcement learning, rather than just kind of these reward shaping stuff that you can only do with games where you win and you lose. Most will be interested in incredible new opportunities for robot and software. Through innumerable self-replicating robot factories in the asteroid belt and beyond, they will transform the solar system, and then within a few 100,000 years, the entire galaxy, and within tens of billions of years, the rest of the reachable universe. Despite the light speed limit, the expanding AI sphere will have plenty of time to colonize and shape the entire visible cosmos. The universe is still young, only 13.8 billion years. Let's look ahead to a time when the cosmos will be 4 times older than it is now, about 55 billion. By then, the visible cosmos will be permeated by intelligence. Because after Omega, most AIs will have to go where most of the physical resources are to make more and bigger AIs. Those who don't will not have impact. Cool. Nice little ending there. You know, he ends with kind of a paragraph on the size of the universe, and then he starts I guess not the introduction, but he starts with kind of the chain rule. 1676. Cool. This was a longer paper, but you know, a nice little summary. Learned a bunch of names. Have more respect for Schmidhuber now, even though he may or may not be a little bit overzealous in his attribution to his own work, but it does seem like he did do a lot more than I thought he did. Yeah. I don't know, we'll leave it at that. Thanks for listening. Probably gonna do streams tomorrow and then Thursday, but then I'm gonna be gone again Friday and Monday, so Sorry for the lack of streams during this holiday period, but I figured this one was kind of an interesting one, little historical lesson for the holidays today. Futurists in the 80s predicted all this, including smartwatches, etc. They have drawings. Ooh. Okay. Cool. Yeah, thanks for listening. Like and subscribe, even though I feel weird saying that because I don't feel like a YouTuber. I feel like I'm just kind of like streaming my life. But yeah, thank you and see you guys later.